Once we've made sure that there's no multicollinearity in our independent variables, we can move on with our multiple linear regression. First thing we need to do, and the rest of the pipeline is going to look very similar to the case of simple linear regression, but the very first thing we need to do is to redefine our x and y variables. Our y variable doesn't change, but we're going to include it for completion, but our x variable changes because we're going to include more independent variables. How many to include? That's an important question, and there's not always a clear answer. I'm going to go back to this paired plot and examine the relationship between all of the independent variables and the dependent variable itself. So I know for sure that I want to include the length of membership because it shows a strong linear relationship. Average session length and time on app, they also show a clear positive relation as shown by this regression line here, but time on website, not necessarily so. So for this analysis, I'm going to choose to leave this variable out because it seems like it carries no predictive power. So let us begin by defining the x and y variables. So here I'm going to subset my data frame and I'm going to include all of these variables. So I want average session length, hopefully I don't have any typos, time on app. I want to leave out time on website and I want to include length of membership. For the y variable, for our dependent variable, it remains the same. This is the yearly amount spent. That's good. Let's add one more cell to check the shapes. So let's let's check the shapes. So we're going to print the shape of x and the shape of y. Perfect. So now we see that we have 3 independent variables. We chose average session length, time on app, and length of membership. So now this is a matrix with 500 rows and 3 columns, and our dependent variable is still a vector with 500 observations. Next, we need to split our data into a training and a testing set. So for that, we use the usual syntax: xtrain, xtest, ytrain, ytest, and this is the train test split of our x and y. We're still going to keep 20% in the test set, and we're going to use the random state equal to 23 for reproducibility. Now, how do we define a multiple linear regression? It's actually the exact same syntax as for the simple linear regression. So we use the same class that we imported for the simple linear regression. The only thing that changes is the x that we pass to the fit method. So these steps are syntax-wise exactly the same as for the simple linear regression case. So we define and fit a linear regression. I'm going to call it linreg. I'm going to call it regression. I'm going to call it mul-lin-reg for multiple linear regression. And this is going to be a linear regression. So this stays the same. And the only thing that changes here is I'm going to fit it as well up here. We're going to fit it with the new x and y variables. And sklearn on its own is going to understand that this is a multiple linear regression. So we just call multiple linear regression fit, and we pass in our train set. It's perfect, and now we can print and interpret the intercept. So let's look at the intercept here. This is very curious. Let's look at the multiple linear regression intercepts. We see a negative value of minus 1029. What this means is the amount of money that we would expect someone with 0 session length, 0 time on app, and 0 length of membership will spend. Now clearly this example is not realistic. Someone that is brand new to the app, has spent no time on the app, and has not attended one of the sessions, we don't really expect them to spend anything. So the intercept here is purely acting as a mathematical tool that would allow us to draw to properly fit our coefficients, but it doesn't necessarily have a physical interpretation itself. However, the coefficients, which we can access with our usual coef attribute, these do carry a physical meaning. So we get 3 coefficients this time, 1 for each independent variable, and we can interpret them in exactly the same way as we interpreted the simple linear regression coefficient. They are in order, so the first coefficient corresponds to the average session length. which, if you remember, this e-commerce platform, they offer sort of in-house tailoring sessions, and this is the average session length. For each minute that they spend on their in-house appointment, they spend $25 more, regardless of how much time they spend on the app or the length of the membership. So we're keeping these two constant, and we're just evaluating for every minute that they spend in their session, how much money are they expected to spend, how much more money. Same for time on app. Now we're going to focus on the second coefficient. This corresponds to the second variable, the time on app. Holding all other constant, meaning regardless of how long they spent on the session and regardless of how long they've been a member for every minute that they spend on the app, they end up spending close to $39 more. And now for the last one, for the length of membership, we know that regardless of what the average session length is and the time on app, for every year of membership that we increase, we expect the customer to spend $61 more. So that's the interpretation of the multiple linear regression coefficients of the different slopes. The key here again is being able to keep the other constant, and now we're confident that we can do that because we have checked that there is no multicollinearity. Moving on, we can, just like before, we can generate predictions for the test set. So I'm going to call this predictions, and I'm going to use the multiple linear regression predict on the X test. Sorry, this is for the train set. I don't really want to do this. We're going to calculate the predictions for the test set, which is the multiple linear regression predict for the X test. And we're going to calculate and print the metrics. Just like before, I'm going to calculate both the mean absolute error and the root mean squared error. So let's define those. The mean absolute error is the mean absolute error between the true values, so Y test and the predictions, and the root mean squared error is the mean squared error between the Y test and the predictions by setting squared equals to false. And let's print those to the screen. So the my is equal to the my, and the root mean squared error RMSE is equal to the RMSE. So the results are quite impressive. Let us go back to compare with the simple linear regression case. In simple linear regression, we got where did we get our predictions? Up here. So in the simple linear regression, by only using the length of membership, we got a mean absolute error of $33 and a spread or a root mean squared error of 42. By introducing these extra explanatory features, we've greatly improved the performance of our model. Now we're achieving a mean absolute error of about $8 with a spread of 10.